RMS value. Now, let us see what is it for our rectifier output. Okay, let us see what is this VDC and VAC for our rectifier output. So for that, first let us talk about the average or DC value. So before proceeding further, first of all, to find out this average or DC value, you need to give an equation representation for our input waveform. So normally when you have a signal, we represent a signal by x of t, and any signal will be having an amplitude and time period, right? So how do we represent a sinusoidal wave as an expression?
Vm sin omega.
Yeah, general notation we use, if it is a sinusoidal signal, we write it as a sin omega t, right? This is the general notation we usually go with. Now, as per our circuit and as per our waveform, what is x of t? It is simply Vi. What is the amplitude A? We
Vm.
are notating it with Vm. Maximum value plus Vm and negative peak is minus Vm. So that means amplitude A is nothing but what we show as Vm. And then we are taking sinusoidal signal. So it is sine. And the x-axis we are taking is the angular time period. So it is omega t. So we write it as Vm sine omega t. Okay. So this input sinusoidal signal, which we have shown as a waveform, is given an expression like this. Vi is equal to Vm sine omega t. Now it is for what period? It is Vm here.
2 pi.
Is it for 2 pi?
What is no? 0 to pi Vm is max.
Yes, that is what you have to write. So 0 less than omega t less than pi. So for this period, it is Vm sine omega t. And what is it for pi to 2 pi?
Minus Vm.
So it is minus Vm sine omega t. So what is that I write? Pi less than omega t less than 2 pi. So this is how you define a signal. Here our input signal. Okay. So Vi is Vm sine omega t for the period 0 to pi minus Vm sine omega t for the period pi to 2 pi. Now on similar lines, how do we define this output?
For only positive half cycle. Vm sin omega t.
So what is x of t now?
Vm sin omega.
X of t. X of t is nothing but V0. Isn't it? So your output exists only for the period 0 to pi. Whereas for the period pi to 2 pi, it is 0. So what is that I can write here? V0 is equal to, the maximum voltage is also Vm here. So what is that I can write? Vm sine omega t, and this exists for 0 to the period pi, right? And what is it for the period pi to 2 pi?
0.
So it is 0. So that is what we write here. So this is how we define our output signal. So once you define this output signal, then start finding out the parameters one by one. So first of all, how do we find out the DC or average component of a signal?
1 by t integral.
Yes, it is 1 by t integral
0 to t.
0 to t.
Vm sin omega t.
So here we write it as V0 d omega t, right? Yes or no?
Yes, ma'am.
Why V0? Because I want to evaluate what is the DC component in my output. So it is V0 d omega t. Now what is our time period t here?
0.
What is t?
2 pi, ma'am, but
Yes, it is 2 pi. Because the output waveform is repeating for every 2 pi period. So time period is defined as what? The time period for which the waveform repeats itself. So for every 2 pi period, the waveform is repeating. But the problem is in that 2 pi period, what is that we see? We see two cases. One is output exists and the other case output doesn't exist, which is 0, as we have written it here, right? So now what is that I can do now? Let us substitute. So it is 1 by 2 pi integral 0 to 2 pi. Let me write it as V naught d omega t. But as I said, our output for 0 to 2 pi is not the same. So for two different periods, the output is changing. So you split this. So what is that you write now? 1 by 2 pi. How can I split? 0
Integral
to
0 to
pi V naught d omega t plus pi to 2 pi V naught d omega t, right? Now substitute what is this V naught for 0 to pi? What is it?
Vm sin omega.
Yes, Vm sin omega t. So 0 to pi Vm sin omega t. Now what is it for the period pi to 2 pi?
0.
So can I write 0 here? Can we write or not?
Yes, ma'am.
Because V naught is 0 for us as per our output expression or output waveform. So finally you are left out with what? Vm sin omega t under the integral 0 to pi. So if you bring out Vm out of the bracket, so it is Vm by 2 pi. And what is integral sin theta?
Minus cos
Minus-
omega.
So minus cos theta. So can I write it as minus cos omega t for the limits 0 to pi? Can we write it or not?
Yes.
Okay.
ma'am.
So now if you substitute the limits, what is the value of that term there?
0
0.
of minus 1.
Minus of what is cos pi?
Minus
Yes.
1.
Minus 1. So it is like cos pi minus cos 0, right? Yes or no?
Yes, ma'am.
So what is cos pi? Minus 1.
Minus
What is cos 0?
1.
1, ma'am.
1. So it is minus 1 minus 1. What is it?
Minus 2.
Minus 2 into minus
2.
2. So finally that means this is simply equal to what? 2 Vm by 2 pi. Yes or no?
Yes, ma'am.
So 2 gets cancelled. So finally what is that you are left out with now? VDC or V average equal to?
Vm by
So it is equal to Vm by pi. Now earlier, as one of your friends said, what is that? For a sinusoidal signal like this, in the same procedure, if I calculate the DC or average component, what it was found to be?
0.
0. Whereas this Vm by pi is what we calculated for our rectifier output. And is it found to be 0?
No, ma'am.
No. There exists some amount of DC component present. And what is it equal to? It is Vm by pi. For example, let us say the waveform has got the maximum voltage of 10 volts, let us say. So what is the DC component present in the waveform? It is 10 by pi. Pi is 3.18. So if you substitute and find out this value, you get that the output waveform has got certain DC component. So which means if I take a sinusoidal wave which has both positive and negative half cycles, then the DC component in such a wave is always 0. But here in the rectifier output, since one half cycle is clipped, okay, so I find the DC component which is equal to Vm by pi. Understood? So why is it 0 here? For positive half, it is Vm by pi. If you calculate in the same way for negative half, it becomes minus Vm by pi. So both gets added. So Vm by pi minus Vm by pi. So totally the DC component becomes 0 for input. Whereas our output has only one half cycle and that positive half. So here the output is Vm by pi. Is this understood now?
Yes, ma'am.
So few textbooks, what they do is, instead of taking the signal as a voltage signal, they take it as a current signal, which means instead of finding out VDC or VAVG, that is average voltage, they try to do it for average current. Okay, they try to do it for average current, which means what? Instead of finding out VAC or VDC, they find out IDC or IAVG. And they do with the same procedure. How? It is equal to 1 by T integral 0 to T. Okay. Instead of V naught d omega T, what they will write? IL d omega T. Now, what is this IL? It is the same. Instead of V, you replace I. Okay. So here IL is nothing but Im sin omega T for the period 0 to pi, 0 for the period pi to 2 pi. And you can go with the same derivation. And finally, what is that you find here? IDC or I average equal to?
I am.
Yes, it is Im by pi. It is Im by pi. Okay. So this is what we see. Or if you know what is VDC, I can calculate IDC. How? If you are aware of VDC, you can calculate I. If you know voltage, how do you find out current?
IR.
If you
Equal
know
to
voltage, how do you evaluate current?
V equal to IR, ma'am. R will be
Now, V equal to IR. I am asking what is I equal to?
V by R.
That is what I want. So it is V by R, right? But what is V?
VDC.
I is IDC. So V becomes VDC. And what is this R?
Same RL.
Right. It is RL. So if you know VDC, easily you can evaluate IDC by writing the expression as VDC by RL. Okay. Or other way is, if I know IDC, how do I get VDC as?
IRL. IDCRL.
IDC into RL. So don't get confused when you refer to textbook. If you find some of them deriving the expression for IDC and then finding out VDC from IDC, it is the same as finding out VDC and getting IDC from VDC. Is that understood?
Yes, ma'am.
So mainly these end expressions, we will be using them while solving the problems. So in rectifiers, problems are equally important as the derivation. So you'll be asked about A bit as a derivation or operation. B bit will always be the problem where you will be asked to determine these parameters. So directly you have to recollect these expressions, go for substitution and evaluate the answers. Okay. Now let us move on to the next one. What is the next parameter?
VAC,
Yes. So what does this VAC indicate?
VRMS,
How much amount of AC component is present in the rectifier output? Okay. So VRMS or VAC is the second parameter. Now, how do you give the expression for this?
Square root of 1 by t.
So RMS
Zero
stands for root mean square, isn't it? So you are calculating the root mean square value of our output waveform, which is the rectifier output. So how is this given by? VRMS is equal to, if you go with the actual definition, it is nothing but square of the
input.
area under the waveform, okay, by the time period. This is how usually we define the root mean square value. Okay, but what is the expression given by?
1 by t integral.
So it starts with the square root. So square root 1 by t integral 0 to t and then v
V
naught
square.
square d omega t, isn't it?
Yes, ma'am.
Okay, so root, this is mean square. So 1 by t integral 0 to t v naught square d omega t. Some textbooks they also use for v naught, instead of v naught they write it as v naught of omega t. Both are same. Okay, so here they are specifying what is the axis. So here I am directly showing it as v naught square. Now what is time period t here?
2 pi.
So that doesn't change. V naught 1 by 2 pi integral 0 to 2 pi. Then v naught square d omega t. Now what is that I have to do? What should be done?
Substitution.
Yes. What is that? I am writing directly, splitting the integral as well as substituting the value of the output. Okay. So 0 to pi, v naught is Vm sin omega t plus pi to 2 pi. What is the value for pi to 2 pi?
0.
0 d omega t.
Ma'am, whole square VM.
Okay. Is it okay now?
Yes, ma'am.
Now, obviously this is 0, so we need not worry about it. So finally you are left out with what? Integral 1 by 2 pi Vm squared, let me bring it out. So Vm squared. So this Vm squared I brought out of the bracket, out of the integral. So you are left out with what now? 0 to pi sine squared omega t. Now what is the integral of sine squared theta?
Minus cos 2 omega t by
Yes. Vm squared by 2 pi. What is it? 1 minus
Cos 2 omega t by 2.
cos 2 omega t by
2.
2 under the limits 0 to pi. Now, can anyone tell me and evaluate what is the value of this? Quickly.
Root pi, ma'am. Overall value root pi.
m square by 4 pi into 2 pi.
Vm square by
4 pi into 2 pi.
from where 4 has come?
Outside.
This
Outside.
2 denominator 2 you brought it out of the bracket, right?
Yes, ma'am.
So it becomes Vm squared by 4 pi. Good. After that,
Into 2 pi, ma'am.
why is it 2 pi?
Substitute to pi and 0 comes 2 pi, ma'am.
Ma'am, we have not done integration, ma'am.
Oh,
Yes,
Ma'am, we have not done integration, ma'am. Directly we have substitute formula.
and that is what you integrate it. That's what I want to do.
Omega t plus sine 2 omega t
You
by 2.
want this, right?
Yes, ma'am.
Okay. Now do it and tell me.
Omega t plus sine 2 omega t by 2.
What is the final one?
Root pi came, ma'am.
So it is Vm squared by 4 pi. So tell me what is the value of this bracket?
Pi, ma'am. Pi.
That is pi. Okay, so what we are to do? 1 by 2 integral 0 to pi 1 by 2 d omega t. So integral 1 d omega t is 1 by 2 into pi minus 0, right? Minus cos 2 omega t. So this becomes 0. So finally you are left out with pi. So pi here gets cancelled. And square root Vm squared by 4. So what is finally the
Vm
value
by
that
2.
you are getting?
Vm by 2, ma'am.
So it is simply Vm by 2. So what is the RMS value or DC component present? Sorry, AC component. It is nothing but Vm by 2. So that means in the rectifier output, which is having positive half cycle like this, there is also what present? Some amount of AC component. And what is that AC component present? It is Vm by 2. Now, if you take an example, let us say Vm is 10 volts. Okay, Vm is 10 volts. So in my rectifier output like this. So what is VDC?
Vm by pi.
Which means 10 by pi, right? What is VAC?
10 by 2.
10 by 2. So this means this is 5 volts. And what is 10 by pi?
3 point something.
Yes, you get 3 point something. Okay. So now if you see in the rectifier output like this, can I say now it is something like pulsating DC?
Yes, ma'am.
So that means I have AC component as well as DC component. In rectifier half wave, but what is that I see? It is more amount of AC when compared to DC. But finally, rectifier output doesn't have only the DC component. It also has along with it some amount of AC component present. Is this understood now?
Yes, ma'am.
1 second. So is this clear?
Yes, ma'am.
Yes, ma'am.
Okay. So now once we have identified the DC component and AC component, let us find out the next parameter, which is nothing but. So next parameter,
Ripple factor.
ripple factor. Ripple factor is represented by
R.
capital R or small r?
Small r.
Small r. Okay. So how do we define this ripple factor? The ripple factor is defined as the ratio of, third one, ripple factor. So I told you what this meant by a ripple. So a small wave-like form is what we call as a ripple. Okay. So this ripple factor R is always defined as the ratio of RMS value of AC component. So already in the previous one, we defined what is the AC component present in the rectifier output, right? So to that AC component, RMS value is the numerator. RMS value of AC component to the DC value of the component. So that means nothing but your VDC. So RMS value of AC component to DC value of rectifier output is given by ripple factor. So the expression for this is VRMS by VDC. It is not VRMS, it is VRMS. So VRMS is RMS component. VRMS is RMS value of the triple component. Okay, so that is given by VRMS. Okay, and this VRMS is given by, or if you substitute or find out this VRMS value, okay, you have a small derivation over here, but I'm giving you directly the expression. So if you find out this RMS value of the ripple component and substitute here and have the ratio of ripple factor, you get it as VRMS by VDC whole square minus 1. Okay, you have it as VRMS by VDC whole square minus 1. So this is what you have it as the ripple factor final expression, which means this VRMS is equal to root of VRMS squared minus VDC squared. Okay, so that is what it is. VRMS is equal to root of VRMS squared minus VDC squared. One second. So if you substitute this VRMS, which is root of VRMS squared minus VDC squared here, you get it as VRMS by VDC whole square minus 1. So ripple factor tells you how much amount of AC component is present in the DC output. That's why we have taken here the denominator. Okay, how much amount of AC is present in the DC output of the rectifier. So it is VRMS by VDC whole square minus 1. Directly you can write this expression and go for the substitutions. So if you substitute, what is that you get? Root of, what is VRMS we obtain?
VM by root 2. 2.
2 or root 2?
2, ma'am.
2, ma'am.
2. By VDC?
VM by pi.
All under square minus 1. So if you simplify, square root of VM gets cancelled, right? So you are left out with what? Pi square by 4 minus 1. Okay. So if you find out this ratio value of root of pi square by 4 minus 1, can anyone tell me what is it equal to? It is equal to 1.5. 1.21. It is equal to 1.21. So what to understand from this value of 1.21? So the amount of ripple component that is present in the rectifier output is very, very high. It is almost greater than 100%. Okay, so that means in half wave rectifier output, more amount of AC is observed and very less amount of DC output exists. Okay, so that is what we need to understand by this factor, which is ripple factor. Okay, so these are nothing but the disadvantages that we see in half wave. So to overcome these disadvantages only, we have gone for the other versions of rectifier, which is full wave, that too bridge and center tap. Okay, so this is about the third parameter R, which is 1.21.